The last part of step 6 has to deal with graphing some linear functions that aren't just one straight line. And in fact, some of these we wouldn't even consider linear, like the absolute value, because it's going to have a bend in it when we get to the absolute value. It's not going to make a straight line, but they're very similar to what we've been talking about. So we thought now would be a good time to talk about some of these types of special functions like piecewise, greatest integer, absolute value. We're going to start with piecewise functions. Now, in our Algebra 2 course here, we are only going to be focusing on linear piecewise functions. So each piece of our piecewise function is going to be a piece of a line. I'm going to show you something in Delta Math today where they are not all pieces of lines. Some will be pieces of quadratics or absolute value functions. But for your quizzes and tests, we will be dealing with all pieces of lines. So for this first example, we have f of x equals, and then it splits off into two different lines. We have a line x minus 2 when x is less than or equal to -1, and the line changes x plus 3 when x is greater than or equal to -1. So in order to graph this, I'm going to actually have two pieces of lines. We're going to start with the first line right here. And I'm just going to graph this line like we always do. We begin with B and we move M, which our slope is 1x. So I'm just going to plot a line going across my graph. I'm going to grab my line feature. And I'm going to draw the entire line. That's the line for this entire green line. But there's a constraint right next to it. It says when x is less than or equal to -1. So I'm going to go over to x equals -1, and I'm going to grab my little eraser, and I'm going to cut the line at -1. This is where x equals -1. I just dropped right down, cut the line. Now I look at this symbol. Think back to when you graphed inequalities on a number line. If it was strictly less than, you put an open dot and then you would shade to the left. Well, I'm going to also put an open dot here. And now I have to decide which piece of this line to keep. I cut it. Now I have to keep only one side of it. I want to keep the side that's less than -1, smaller than -1. Which side of this line is smaller than -1? Right here. Which means I'm going to get rid of the other part of the line. It's no longer part of my graph. This part right here is this green line only when x is less than -1. It's right here. So now I'm going to do the other line. I'll call it my yellow. I'm going to graph the whole line again. I'm going to begin at 3. I'm going to go up 1, right 1, slope of 1 because it's 1x, down 1, back 1, putting a couple points on my lines so when I grab my line feature, my line tool, I can connect them. These lines are parallel, which we expect because they have the same slope. All right, now, again, I'm going to grab my small eraser and I'm going to break the line that I just drew at -1. So here's -1, I go up and I break it. All right. I want to put a closed dot right where I broke it because this is greater than or equal to. So I put a closed dot. And now I need to erase part of that line that I just drew. I want to keep the part that is greater than -1. This part right here is where x is greater than -1. So I'm going to erase the other part. And now I'm finished. I've graphed this piecewise function. This is not the only way to graph a piecewise function. And in class with your teacher, we will be doing other ways to graph a piecewise function. Let's work backwards. Now we have a picture and we want to write what that function was that created this graph. So we know we can say f of x equals, but it's not just one line, it's going to be 3 different lines. So we put this bracket in place. And I'm going to number them. We have the first piece, the second piece, and the third piece. We need to write an equation for each piece. Well, we've been doing this a lot. We know how to look at a graph and write the equation of that line. Just pretend this line goes on forever. That's what we're going to do first. We know that the slope of this first line, we go up 2 over 1. We know the slope is 2, and we know the y-intercept of this first line is right here at 3. Let's take a look at the second line. Imagine this line going on in both directions. Right now it's just a little bitty segment. We know the slope of this segment though because we have 2 points on it. We go down 1, right 1, so I know it's negative x. Where would it cross the y-axis? Where would the y-intercept be? Imagine drawing this line further out. It would cross right here if I continue my slope at 2. And now for the third piece. The third piece is just a horizontal line. Remember, f of x is function notation for y equals. What does y equal everywhere on this third piece? Y equals 3. That's the horizontal line. Y equals 3. Now we just need to put the constraints in. For the first one, x, it's not everywhere, it stops right here. This is where x equals 1. My line is all of the spots before I get to x equals 1, and then it stops, and there's a hole, and it stops going. We reach a dead end. So less than 1. Now this piece has 2 endpoints. It's between here and here. This is when x is 1. This is when x is 2. So it's between 1 and 2, but it includes these endpoints, so we put a line under them. And then finally, my third piece starts right here. This is when x equals 2 and goes on forever. So x is greater than 2. And that's how we work backwards to write the equation of a piecewise function. Let's talk about the greatest integer function. This function looks like 2 brackets and the x and then 2 more brackets. It just means that instead of making a nice straight line, it's broken up into little steps. Sometimes we call this a step function instead of a greatest integer function. This symbol literally means the greatest integer less than or equal to x. So if we think about a number line, here's 0, here's 1, 2, 3, 4, 5, 6. 3.25 would be right about here. But the greatest integer would be biggest integer before we got to this point, which in this case would be 3. What about this one? Negative 4.6. Well, that's going to be off on the negative side. Negative 4.6 would be about here. What is the greatest integer less than this? It would be right here, negative 5. This makes a lot more sense when we talk about a real-world example problem. This is a very common scenario. An automotive repair center says that you're just going to pay $50 just for bringing your car in, no matter what. Even if you just bring it in, drop it off, pick it up right away, it's going to be $50 for any part of the first hour of labor. And then they're going to charge you $35 every additional hour. Now, if they work for an hour and 15 minutes, they're not going to charge you $50 in part of the $35. They're going to charge you the full $35, which is why we can't write y equals 35 per hour plus 50, because that implies that they're only going to charge you part of the 35 if you're there for, say, an hour and a half or part of an hour. But that's not how this scenario works. So we can't just draw a line like we normally would. We need to actually draw a step function or a greatest integer function. Notice that between 0 and 1, you're going to get charged $50. Between 1 and 2 hours, you get charged the $50 plus 35 for a total of $85. Anywhere between 1 and 2 hours, you're going to pay $85. So right away, we jump up to $85 and we stay there all through that first hour until we get to hour 2. Then we jump up and it starts costing us $120 and so on. So what does this look like on our graph? Well, I'm going to put time across the x-axis in hours. Now I know your graph in your notes has 4 quadrants, but you can either screen grab mine that only has 1 quadrant, or you can just focus on your 1 quadrant. Because we're talking about time, so we know it's going to be positive x's, and we're talking about cost. They're not going to give you money to work on your car. So the cost is going up here on the y-axis. This would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my money, I'm going to count by 50s. 50, 100, 150, 200, 250. Actually, I could probably go back and count by 25s instead. Let's count by 25s. All right, now that we have our graph set up, let's plot what happens in this scenario. Between 0 and 1 hours, we pay 50. And we don't include 0 because at time 0, it doesn't cost us anything until we bring the car in, up until an hour. Then it jumps up to 85. And you pay 85 all through that next hour until you get to 2 hours. Then it jumps to 120. And you pay 120 all the way until you get to hour 3. At hour 3, it jumps up to $155. And you pay $155 all the way through that hour until you get to hour 4. And finally, $190 for that next hour. And you would continue to just keep adding 35 and drawing across the next hour as long as you need for your entire graph. That's greatest integer. And finally, let's talk about absolute value. We know what absolute value means. For instance, if I say the absolute value of 8, it's going to be 8. The absolute value of 5 is going to be 5. The absolute value of negative 2 is going to be 2. Absolute value is always positive. We know that from years back when we talked about absolute value for the first time. But what does the graph look like? When we graph absolute value, x is always going to, whatever we put in here, when we take the absolute value of it, y is always going to be positive. So we know it's always going to be going up in both directions here. This graph is V-shaped. The domain is all real numbers. The range is when y is positive. And we're going to talk about these two features a little bit more when we get to some of the graphs. So how would we graph something that looks like this with absolute value? Well, one of the best ways is to use your graphing calculator or flip over to Desmos and type this function in, absolute value of 2x, subtract 4. Absolute value is right down here. If you don't see your keypad, you can open it up. Absolute value of 2x, subtract 4. I'm going to get rid of my keypad. Here's my graph. I just need to copy this graph onto my graph in my notebook. I know the y-intercept is 0, -4, so I can start by plotting that point. But then I need to figure out how to graph the rest. Well, if you just click on this gear right here at the top and click on the table, it'll give you a really nice table of points. And you can even add points to this table. Let's say you want to go past 2 and -2. You can do that. Let's start with these points because these are all 5 really nice points. So -2, 0. We'll put that on our graph. And then we also have the point -1, -2, which is right here. We have the point 1, -2. We have the point 2, 0. That's really enough points to draw in the rest of this graph, but if you want more, let me show you. You would just type a 3 and it tells me 3, 2. And if I hit enter, it tells me 4, 4, and so on. So I can get more points on my graph from my table. Now I'm going to connect these. I'm going to start here and draw a line. Then I'm going to do it again. Let's start here and draw a line this way. And I've graphed my absolute value function. Now let's talk about the domain and the range. To find the domain, we want to know all the possible x values. So I'm going to start on the left, right here on the x-axis, and I'm going to highlight where there's graph. So there's graph above me right here, there's graph above me, I'm hitting the graph, there's graph below me right now, there's graph below me, there's graph above me, there's graph above me. But even though my line stops because my graph stops, it goes on forever. So I know I could actually keep on going. Same thing to the left. That line goes on forever. So when would I stop highlighting my x-axis? I never would. So my domain is going to be from -infinity all the way to +infinity. Now this is interval notation. That's how we write all the possible numbers. Let's talk about the range. The range, you guessed it, is all the possible y values. So I'm going to do the same thing again. I'm going to get rid of my yellow highlight right now. Let's look at the y values. I'm going to start where I see the graph. There's graph to the left and right of me. There's still graph to the left and the right of me. There's still graph, all the way until I get to here. And then I stop because there's no graph down here. This is when y is bigger than -4. So to write my range, I'm going to start at -4. It can be -4. See, there's a point right here at -4. And then it goes on to +infinity. So that's how I find my domain and my range.